Okay, so in this example problem, we're examining a conical viscometer, shown here, which attempts to measure the dynamic viscosity of some arbitrary oil of viscosity mu and film thickness d. The viscometer has some applied driving torque T, shown here, and that applied driving torque results in some angular velocity omega and angular acceleration alpha. The major radius of the viscometer is r, the major height of the viscometer is h, and the viscometer's angle with the vertical is theta, shown here. Now our assumptions are as follows. 1, we're assuming that the oil is a Newtonian fluid. 2, we're assuming that the flow within the oil is incompressible and laminar. 3, we're assuming that we have a small gap width d. 4, we're assuming that we're going to neglect aerodynamic drag. 5, we're going to assume that we are in steady state. 6, we're going to assume that we have planar symmetry about the axis AA. 7, we're going to assume that theta is less than 90 degrees. And 8, we're going to assume that horizontal velocity profiles develop in the oil of width d. So we're going to assume that these red horizontal lines here reflect how the velocity profile develops within the oil as the conical viscometer spins. Okay, the objective of this problem is to express mu, the dynamic viscosity of the oil that we're testing, as a function of known variables. So as a function of t, d, theta, omega, and h. So the first step of this problem is we draw a free body diagram of the viscometer where we're only going to express angular quantities. So here you see that our conical viscometer is shown about the axis AA. We have our T applied torque spinning counterclockwise, and we have our TF, which is equal to the integral over A of r tau f dA, which is the resistive torque due to viscous fluid action. So the applied torque goes in one direction, and the viscous torque goes in the opposite direction. It opposes motion. We're assuming that the angular velocity omega is counterclockwise, and the angular acceleration alpha is also counterclockwise. So what we're going to do then with this free body diagram is write out Newton's second law for rotation, which we have here on the right. So we're going to assume that our counterclockwise direction is positive, and we're going to sum our torques about the axis AA, which is then equal to the moment of inertia of the conical viscometer about the axis AA times the angular acceleration of the conical viscometer about the axis AA. Remember that we're in steady state, so the alpha AA term goes to 0. And then we just have the sum of our torques about AA is equal to 0. So since we have our applied torque going counterclockwise and our viscous torque going clockwise, we can then write T minus TF is equal to 0, where remembering T and TF are both magnitudes because we've manually applied the sign here as negative. So basically what Newton's second law then says is the applied driving torque is equal to the resistive viscous torque, or the magnitude of the driving torque is equal to the magnitude of the viscous torque. So now the question is, how do we calculate the viscous torque, TF? So here on the left we show our conical viscometer, which is in yellow, we have our wall, which is in white, and we have our oil, which is in blue. The points in red are the points along the conical viscometer, and the points in green are the points along the wall. Remember that we're assuming a horizontal velocity profile developing in the oil, so we have these horizontal blue lines to represent the velocity profile in the oil. You can kind of imagine that the velocity profiles, as shown here, are going into the page on the right-hand side of the conical viscometer and out of the page on the left-hand side of the conical viscometer based on the direction that we've assumed the conical viscometer is spinning, in other words, counterclockwise. So then if we break out this velocity profile, just some arbitrary velocity profile, and then look at it from a top view instead of a side view, then we can kind of see that this green point is on the wall and this red point is on the conical viscometer. The no-slip condition says that this green point has to have a 0 velocity, and this red point has to have a velocity equal to r omega, where r is the radius of the conical viscometer at any given z, and z is the height of the conical viscometer at any given r. So if we were to look at this velocity profile right here, we'd come up here, and this would be our z, and then this would be our r. So because again of the no-slip condition, our velocity at the conical viscometer within the oil is r omega, and our velocity at the wall is 0. Because we've assumed a small gap width, we can assume a linear velocity profile between these two boundary conditions, and that's why we have a straight line connecting our 0 and r omega velocity vectors. We're going to call our velocity profile within the oil little u, which again we assume is linear. Now what we're going to do is, if we go back to our previous slide here and we see that we've defined the magnitude of our viscous torque as an integral, we're going to probably want to start breaking down some of our differential relationships to prepare to plug them into the integral later on in the problem. So if we look at our z and r as defined here, we can come up with some simple geometric relationships such as r is equal to z tangent theta, or dr is equal to dz times tangent theta, and z is equal to L cosine theta, and dz is equal to dL times cosine theta. These geometric relationships, which just come from this definition right here, this triangle right here, which adheres to these definitions right here, these geometric relationships will come in very handy when we get to the integral part of our problem. So moving on to the next slide, we can kind of break down that velocity profile from the top view that we saw in the previous slide and use it to calculate the shear stress within the oil, which we can then use to calculate the shear torque on the viscometer. So on the right, we're just going to look at the general form of our Newton's law of viscosity, which we have previously called the time-dependent form of Newton's law of viscosity. And that just says that the magnitude of the viscous shear stress within the fluid is equal to the dynamic viscosity of the fluid times the magnitude of du dy hat, where du dy hat is a partial derivative. And we'll note that y hat is just some arbitrary local coordinate system within the fluid, defined from BC number 1, which is defined with no slip, to BC number 2, which is also defined with no slip. So in other words, the local coordinate system just goes from our first boundary condition to our second boundary condition, which in this case, in our case, both boundary conditions are defined with no slip. So our local coordinate system will go from the wall to the conical viscometer. So no slip at the wall, no slip at the conical viscometer. Our local coordinate system goes from the wall to the conical viscometer. And that's why we have y hat, which is positive up to the conical viscometer, defined as 0 at the wall. So one last note. Newton's law of viscosity, as it's written here, applies uniquely at every point along z, or in other words, it applies uniquely along each velocity profile. So if we go to the previous slide, we'll see that our velocity profiles are shown in blue and connected by these red and green dots. Newton's law of viscosity will apply uniquely to each and every one of these velocity profiles. So we can apply Newton's law of viscosity to this profile, to this profile, to this profile, etc. And so what we can imagine is that the shear stress at this profile is not necessarily the shear stress at this profile, or this one, or this one, or this one. There may be a distribution of shear stresses in the oil as a function of z. Now the question is, how do we determine what the shear stress is as a function of z? Well, the way we do that is by applying Newton's law of viscosity to each profile. And the way we do that is by writing out Newton's law of viscosity as a function of z. So that will be our next step. But before we get to that, we need to kind of formalize what the velocity profile for some arbitrary profile is within the oil. So if we imagine that, again, we have our 0 at the wall and r omega at the conical viscometer, which applies to every velocity profile no matter where you are in z, then you can determine that the overall velocity profile looks something like little u is equal to r omega over d times y hat, where r omega, again, is the velocity at the conical viscometer, d is the thickness of our profile, and y hat is our local coordinate system. And the way we know this is correct is because if we plug in y hat is equal to 0, or y hat is equal to this line right here, then we get y hat is 0, 0 times r omega over d is 0, or little u is 0, as it should be, because of the no slip condition. Now if we plug in y hat is equal to d, the full length of the profile, then we get r omega over d times d, the d's cancel, and you get u is equal to r omega, which it should be because of the no slip condition. Now we can play a game because we know that r is equal to z tangent of theta from our geometric analysis. As you can see, r is equal to z tangent theta. So then we could just plug z tangent theta in for r, and we get z tangent theta omega over d times y hat. And so this is the velocity profile for any given profile in our oil. So now we're at a point where we know what Newton's law of viscosity is, and we know the only unknown in the equation, the velocity profile, little u, is this equation right here. So all we have to do is plug in this expression into Newton's law of viscosity and simplify. So plugging in u into Newton's law of viscosity gives you mu times the absolute value of d dy hat of the expression for the velocity profile that we just determined. And here you can note that z tangent theta, omega, and d are all constants relative to y hat. So we can pull that out of the derivative entirely, and then we get d dy hat of y hat, which is equal to 1 times this expression right here, which ends up getting us overall mu times the absolute value of z tangent theta omega over d. Now we note that since we assumed omega is positive all the way back in our free body diagram, we see that this is the positive direction. We've assumed that omega is positive. Then we go to our absolute value and see that z is defined as always positive. It's the height of the conical viscometer, basically, starting from the point. Tangent of theta is positive. We've assumed that theta is less than 90 degrees. Omega has been assumed positive. D is a distance. And so this quantity is already positive. So we could just say that tau f, or the viscous shear stress within the oil at any given z, is equal to mu z tangent of theta over d times omega. And one more time, it's worth noting that the magnitude of the viscous shear stress within the oil is indeed a function of z, as shown here. And that's because it has to be. The tangential velocity of the conical viscometer is higher at the top of the viscometer than it is at the bottom of the viscometer. So due to the no-slip condition, the velocity profile at the top of the viscometer is of a higher magnitude on average than the velocity profile at the bottom of the viscometer. Now, to begin to use this equation, we need to find a way to unpack dA in terms of quantities that we can integrate. So to unpack what a differential area looks like, we need to actually draw a differential area on the conical viscometer. So if we look at the conical viscometer on the left and we look at a differential area with a differential z, just like this, so we just look at a little differential z here, then the first point in our differential z is of radius r, and that's just this point right here. And our second point of our differential z is this point right here, which is of radius r plus dr. Because if you go just a distance r in the second point, you only get to here, you need a differential r, a little extra r, so to speak, to get to the conical viscometer edge. So this is r plus dr, and this is r. So if you then cut this strip 360 degrees all the way around the conical viscometer, so we're basically just cutting out this whole segment of the conical viscometer, and then we unwrap that cylindrical result, we get a planar shape that looks something like this, where the lower segment is of length 2 pi r, and the upper segment is of length 2 pi times the quantity r plus dr. And the height of this strip is dl, as you can see here. Now what we'll note is if we look at this little triangle, and we kind of blow that out down here, this is our dr that we talked about, the little differential r that we need to make up the difference between these 2 points in radius. And this length is dl, and we have our angle theta here. We see that dr, the differential radius, is equal to sine theta dl. And we know that sine theta is less than 1 because of our assumption that theta is less than 90. Now, if dl is really, really, really small, as we assume it will be, then dr is even smaller. So as dl approaches 0, dr approaches 0 even faster. So then essentially, if we're using a very, very small dl, which we're going to if we're using an integral, then we're just going to assume that dr is approximately 0, because dr is just that dl times sine of theta, which is less than 1. So again, if dl is small, dr is even smaller. If dl is going to 0, dr is going to 0 even faster. So we're just going to assume that this dr is 0. Now, if dr is 0, then the length of this top segment is simply 2 pi r. So as dl approaches 0, this little oblong strip actually approaches a rectangle. So as dl approaches 0, this shape becomes a rectangle. And what's the area of a rectangle? Well, it's 2 pi r times dl. So dA, we could just say, is approximately 2 pi r dl. So this is definitely one of the more confusing parts of this problem. So I would encourage you to stop for a minute and really think about what we just did. So we started with this equation, and we know that we need a differential area to use this equation. So how do we determine a differential area on this conical viscometer? Well, you draw a differential area. We decided to draw a differential area with a differential z, and then we unraveled that differential z by cutting this segment out of the conical viscometer and unwrapping it and coming up with this skew shape right here. And then we came up with a limiting argument saying, well, the length of this top segment approaches the length of this bottom segment as dl approaches 0. So if this top segment is of the same length of this bottom segment, then this is approximately a rectangle. This differential area is approximately a rectangle. And so dA is just length times width, or 2 pi r times dl. So finally, we have our equation as we just had written here, the integral over a of r tau f dA, integral over a of r tau f dA, except now we know what tau f is from this slide right here. It's mu z tangent of theta over d omega. So we have mu z tangent of theta over d omega times our differential area, which we know is 2 pi r dl from the previous analysis. So at this point, we're simply substituting in the values that we know and going along with the integral. So you'll note that, again, this was from the previous slide, this dA value, and these two values, dl and r, are just from looking at this triangle that we looked at a few slides ago right here. Okay, so with that being said, let's perform the simplification and the integral. Okay, and writing out this integral, we get this is equal to the integral from L0 to L1 of r mu z tangent of theta over d omega. dA is equal to 2 pi r dl, and that's why we changed the limits of integration here, because we express this integral now in terms of L. And then we could say that that is equal to the integral from 0 to h of r mu z tangent theta over d omega 2 pi r. We know that dl is equal to dz over cosine theta. And again, we change the limits of integration because we are now expressing this integral in terms of z. Integral from 0 to h of r, which is z tangent theta, and then mu z tangent theta over d omega 2 pi r, again, which is z tangent theta, and then we have 1 over cosine of theta dz. Now we're going to note that we have a lot of constants here. So let's see here. We have 2 pi, we have mu, we have omega, we have tangent cubed of theta. That's all over d times cosine theta multiplied by the integral from 0 to h of z cubed, right? Because we have z, z, and z. So z cubed with respect to z, that's equal to 2 pi mu omega tangent cubed of theta over d cosine theta. And this integral is simply z to the fourth over 4 plus some integration constant evaluated from 0 to h. And this is equal to 2 pi mu omega tangent cubed of theta over d cosine theta h to the fourth over 4. And this is equal to TF, or the magnitude of the viscous torque, which is equal to the magnitude of the applied torque. So remember, the magnitude of our viscous torque, TF, is equal to the magnitude of our applied torque, T, and that's from our Newton's second law for rotation. So what we can then say is this is equal to 2 pi mu omega tangent cubed of theta h to the fourth over 4d cosine theta. We have a simplification here. That becomes 2. That becomes 1. And so we have t is equal to pi mu omega tangent cubed of theta h to the fourth over 2d cosine theta. And now we just solve for mu. Mu is equal to 2d cosine theta t, just like that, 2d cosine theta t over pi omega tangent cubed of theta h to the fourth. And this is probably a little bit more clearly expressed as 2dt cosine theta over pi omega h to the fourth tangent cubed of theta. Just like that, okay? So this is our final result. This is our dynamic viscosity of our oil. So as we can see, if we apply a torque of magnitude T on this conical viscometer, and our conical viscometer has an angle theta with the vertical, and a film thickness D, and an angular velocity omega, and a height h, we can determine the dynamic viscosity of our oil mu. So these would all be designed or measured quantities. So for example, D, theta, and H would be design quantities, and T and omega would be measured quantities. And based on this equation right here, we could determine what the viscosity of our unknown oil is. Okay, so that should be it for this example. I really appreciate you watching. Thank you very much, and I will see you next time.